Are you working?
Let's see. Fantastic, yeah, I can see it. Lovely.
The screen is fine and everything?
Yes, everything's good.
Okay.
All right, why don't we get started? Hello, everyone. Thanks so much for joining us as always. It's my absolute pleasure to have here Uyterlinde to present hyperbolic concept bottleneck models. Daniel's in the University of Amsterdam, and you are currently a master's student, is that correct?
Yes, correct.
Awesome.
I just handed in my thesis last week.
Nice, congratulations. Very,
Thank you.
very exciting stuff. Okay, so yeah, take it away, please.
Yeah, okay, so thanks for inviting me. My name is Dan.
For some reason, your screen is not sharing anymore. Is that?
Okay, wait. How about now?
There you go. Yeah, cool. Go for it.
Okay, so yes, I'm excited to talk about my project I did during my master's program at the University of Amsterdam on hyperbolic concept bottleneck models. I did this project together with Swasti Misha and Pascal Mettes. So yeah, and if at any point anyone has a question, just you can just interrupt me because I can imagine some things might be unclear. All right, so I'm just going to quickly go over this because I assume you all know what CBMs are. But concept bottleneck models, the idea is to constrain the inputs to the classifier to be a set of human understandable concepts. So we usually have three components, a feature extractor to get our embeddings. And then from these features, we map to a concept bottleneck layer in which every neuron in this usually linear layer represents a single human interpretable concept. And finally, a linear classifier predicts the correct class. And then we can take we can clearly see which concepts the model has used to reason to get to its conclusion. The problem, however, with current CBMs is that they often model concepts as being independent, while in reality, they're often not. In reality, they're often structured into hierarchies. So you can imagine in a CBM if the concept for Persian cat should be active. This also implies that cat and animal and entity should also be active. You can imagine that concept independence in this way can lead to logical paradoxes where this is not the case. So where cat is active but animal is not. And this cuts the same way for interventions, where if we would intervene on the word or the concept animal, we would also want the concept cat to be deactivated. But standard CBMs don't have this mechanism by default. And to add more to these problems is that Euclidean geometry is not able to accurately embed tree-like hierarchical structures. As you can see in this example here, the amount of nodes in this tree with a branching factor of 2 grows exponentially with the radius. So you can see in this final circle here where you have, I think, 4 layers of nodes, that the outer ring gets really cramped and it's hard to embed these leaf children with little distortion, especially if your graphs become very large. Hyperbolic geometry provides a solution for this. To give you a short recap or a short summary on what the hyperbolic geometry is, hyperbolic space is defined as a Riemannian manifold of constant negative curvature. So as opposed to Euclidean space, in which we all live in, it's perfectly flat with 0 curvature. Hyperbolic space has negative curvature. So you can see in this example on the top right, this is the Lorentz manifold. And the key thing here is that volume grows exponentially with the radius. So so there's 2 popular models of hyperbolic space. The first of which is the Poincaré model, which is demonstrated by this figure by MC Escher. And if you were to imagine this is a hyperbolic space, then all of these fish-like things would be of equal size. So the distances grow exponentially as you get further closer towards the boundary. The Poincaré and Lorentz models, you can actually see this here is the Poincaré model. It's a 2D projection of a 3D Lorentz manifold. And this would then be the Lorentz manifold. Of course, we are working in 500 dimensions, but then the Poincare disk is just a projection of one fewer dimension. And this exponential volume expansion makes it highly suited for embedding tree-like structures. As you can imagine, if we would go back to this, this tree, if the space that's available grows exponentially, you can easily fit all of these nodes in there. And to just show you how counterintuitive hyperbolic space might be, is that in this figure on the bottom left, all of these black lines are parallel lines to the blue line you see here. Hyperbolic deep learning is becoming increasingly popular. So it all started in around 2017 when Nickel and Keela demonstrated the potential of hyperbolic deep learning in a WordNet reconstruction task. So the task here is to reconstruct WordNet based on learned embeddings. And you can see that if we only have 5 dimensions available, that a Euclidean model scores rank 3,500, while the Poincare embedding score 4.9. So really a really big difference. These days there's fully hyperbolic neural networks. So think of ResNets where every component is built on hyperbolic operations. Addition, multiplication, all of these things.
Daniel,
Yeah.
Your screen stopped sharing.
Okay. I can maybe also just keep it as a PDF. Maybe this works better.
Let's try it. Yeah, we can see
Is
that.
this okay too?
Yes, it's
Yeah.
perfect.
Okay. So yes, these days we have fully hyperbolic neural networks, but also semi-hyperbolic neural networks, of which this is an example where we embed a graph into hyperbolic space. And then using the logarithmic map, we can make a tangent space approximation of this graph, do our normal Euclidean operations there, and then using the exponential map, sort of wrap it around this hyperbolic manifold again. So yeah, hyperbolic deep learning is highly effective in low dimensions, and especially for embedding tree-like structures. The one thing that most hyperbolic vision language models are based upon is the concept of an entailment cone. And this is also going to be very relevant for our method. And the idea of an entailment cone is basically that a general embedding should geometrically entail specific ones. So if you have a root concept that's very general, it should entail all its descendants, basically. And the way these hyperbolic vision language models you see on the right, so this one is Meru, it's the first one actually, and it's basically optimized to it works on the assumption that text is more general than an image. So you can think of, for example, the word apple could be described by a lot of different images of apples. So we say the text embedding of the apple is should entail all the image embeddings that depict an apple. HypCBM then, which is the encoder we use in this work, extends this to also include text-to-text hierarchies and image-to-image hierarchies, so that a specific image should be entailed by an image that's more general. This results in naturally hierarchically structured embeddings without explicitly supervising towards this. And yes, crucially, distance from the origin encodes specificity. So you can imagine if we embed a tree in hyperbolic space, that the root concept will be closer to the origin. And we can see this back in the norm of the hyperbolic embedding. So we're working in the post-hoc framework. And under this also falls the label-free CBM. You probably have heard of it before, but the idea is to either query an LLM or use a predefined concept bank to get relevant concepts for each class. Then we encode all of these concepts with a multimodal text encoder, which usually is CLIP in the literature. Then we encode an image with the same multimodal encoder, and then we compute the cosine similarity between this image embedding and all of the concepts in our concept bank. This gives us activations that are bounded in between -1 and 1. And we can now train an interpretable linear classifier on these activation factors. And this way we can turn any vision language model into an interpretable CBM without retraining. So the thing we replace in this work is we replace the activation mechanism to be hyperbolic instead of based on cosine similarity. And we use hyperbolic VLMs. The rest all stays the same. So we use the same concept bank, same classifier, same evaluation, such that any improvement or differences we see are directly attributable to our geometric formulation as opposed to additional trained modules or extra supervision. To prevent information leakage, where a model could just activate all concepts with very tiny activations, we evaluate with ANEC K, so accuracy at K active concepts, which basically measures, okay, if we only have, for example, 5 active concepts, then what's the accuracy? Our concept generation and encoding step is the same as the label-free CBM, but with a hyperbolic encoder. So in our case, HypCBM. The thing we do here is that we generate relevant concepts to our classes. We encode this with our hyperbolic text encoder, and these become the concepts that live on our hyperbolic manifold. Then we do the same thing for our target image. We encode it with our hyperbolic vision encoder, and we get an image embedding Z. The one thing we do different here is that we filter out generic concepts. And the reason we do this is that generic concepts like object and entity, especially if you consider a dataset like ImageNet, I think these two will probably activate on every image, making it hard to, it basically lacks any discriminative power then. And if you can recall, concepts with a low norm are very general concepts, so we filter those out. So this way, like only based on the norm of a text embedding, we can see
Daniel?
whether it's...
I'm
Yeah.
sorry. The screen stopped sharing again.
Okay, I'll just keep
Sorry,
trying.
not sure what's going on. Just randomly
It
crashing.
was very exciting for a moment.
Yeah. There you go now.
Okay. Yeah, just let me know whenever whenever it stops sharing. Maybe I need to... Okay. So we filter out generic concepts by only looking at their norm, basically. And then a few important properties of entailment cones. The two main defining things we're going to need are the half aperture, which is this angle over here. And this angle is inversely proportional to a concept's norm. So this C here is the curvature of the manifold, so how quickly distances grow. And this K is a constant, and this is the norm of the concept embedding. So very general. Yeah.
I'm sorry. I don't know what's happening.
Maybe I can...
I think you stopped sharing entirely, so that's what it's cutting.
Does this work now? I can maybe just keep it like this. Maybe that works.
I mean, works.
Yeah, we can see it.
Okay, great.
Not entirely sure what's going on, but we can try this way.
Okay. So, and the exterior angle basically measures, does this image embedding fall within the entailment cone of a concept? Then additionally, we have this variable eta image, which scales this half aperture, which basically works as some sort of strictness, strictness variable. So with this, you can imagine that some data sets use very specific concepts, like if we did the CUB 200 bird classification data set, there we have concepts like spotted wing or white-gray under feather. Then these concepts will have very high norms and therefore have very narrow cones. So this allows us to scale those up a bit such that we have image embeddings that fall within the cones in any case. The important thing here to note is that the entailment relation is satisfied when this exterior angle is smaller than the scaled half aperture. And as you might have thought of, we define an activation as the margin of inclusion of an image within the entailment cone of a concept. So this activation is maximized when this image embedding falls right in the middle of this entailment cone. And crucially, also when this image embedding falls outside of a cone, then the activation is 0. And this all results in activations that are naturally sparse, because often you will have that image embeddings don't fall within the entailment cone of a concept. They're also non-negative. They're hierarchy aware, because in the way these hyperbolic VLMs are trained, you will always have that Persian cat will be entailed by cat, will be entailed by animal, and so on. And then we also normalize by half aperture to make sure that generic and specific activations are at the same scale. So then we embed all of our concepts onto our hyperbolic manifold. You can see these are the concepts with their entailment cones radiating from it. And we encode an image, and then we just look, okay, how far inside of each entailment cone is this image embedding? Then we can achieve the desired sparsity in our linear classifier by just modifying the regularization weight. And that way we can achieve the desired sparsities. And then we also introduce hierarchically faithful interventions, where an intervention on a parent concept is automatically propagated to its entailed children. You can see in the bottom right here an example of this. So in this case, this child concept is entailed by the parent, and thus we also disable this concept when we disable its parent concept. And just like we had a strictness parameter for text-to-image entailments, we also have a strictness parameter for text-to-text entailments. So we determined this value dynamically because you can imagine, because hyperbolic space grows exponentially, that a single fixed strictness is not sufficient. So we mined, I think, around 10,000 WordNet parent-child pairs, and then we looked, okay, what's the strictness parameter we need to separate true entailments from false positives, and we found that this scales linearly with the norm or the depth of this parent concept. Okay, so we our main goal was to evaluate the differences between Euclidean and hyperbolic CBMs, but strictly in the post-hoc framework, so without any learned modules or extra supervision. We tested for accuracy under sparse concept budgets to answer the question, does hyperbolic geometry actually help with interpretable classification? Then we also measure hierarchical consistency to make, so hierarchical consistency we define as is a child concept active, then the parent should also be. Then we do something similar with intervention efficiency. We see if we intervene on a certain concept, does the prediction to the misclassified class respond appropriately? And then finally, we also evaluate robustness and concept stability under corruptions.
You got cut off.
Daniel, so sorry.
No,
Cut off again.
it might be my fault as well.
I think all internets are going crazy today.
It's just the heat wave. Just,
It probably is, yes. All
there
right.
you go.
Is it visible again?
We can see it again, yeah.
We can see.
Yeah, then I'll just do full screen because it doesn't really matter anyways. Okay, so our main evaluation was accuracy at k active concepts. And we compare against first, okay, so these hyperbolic VLMs are trained on 20 million image pairs because we don't really have an OpenAI type company working on these models. So so yeah, we have a HypCLIP, our encoder with 20 million pairs, and we have a CLIP model that's trained with the same data set. So only these three are directly comparable. And then we also include the OpenAI CLIP baseline as a reference point. And yeah, we compare the label-free CBM.
Daniel?
Yes. Sorry.
I hate to interrupting you.
Yes. Okay. So we compare the OpenAI baseline to our hyperbolic model to also as an ablation LFCBM with this HypCLIP encoder to make sure that the gains don't only come from using this encoder. So this basically is HypCLIP with a cosine similarity activation. And yes, you can see that at all sparsities, our method improves over the baselines. And most interestingly, it also outperforms OpenAI's CLIP at several points. So if we take as an example this, let's look at, okay, so this accuracy at 20 active concepts on the Sun 397 dataset, which is a hierarchical scene understanding dataset, that we outperform the OpenAI baseline by 7%. And these gains are visible throughout the entire table. And yes, this sort of ablation of LFCBM with our HypCLIP encoder scores pretty poorly. And I think this demonstrates really well that we need compatible activation functions in order for us to be able to turn our VLMs into interpretable models. Then we also evaluated data efficiency. So how efficient are the models when we only present them with 1, 10, or 100% of the training data? And I think the most interesting point here is that at this point where we only use 10% data, training data, we match the performance of the LFCBM or baseline, Euclidean baseline, that uses all of the training data. Then, the way we evaluate this hierarchical consistency, I briefly mentioned it before already, but if a fine-grained concept is active, its parent must be too. So we count the amount of hierarchical violations where a child is active but a parent is not. And then we do 1 minus this score in order to get a percentage. And you can see that, oh yeah, one more thing. Since our models activations are naturally sparse, so a lot of them are 0, we can very easily define a concept as being active or inactive, because if it's not non-negative, then or non-zero, then it's active. For the Euclidean model that uses cosine similarity, this is a bit more difficult because the activations range from -1 and 1. So the thing we did was we looked at the amount of activations our hyperbolic model has, and then tried to match, and then we match that average sparsity. So let's say our hyperbolic CBM at this strictness has 500 activations, then we choose the top 500 activations for the Euclidean baseline, and then think of the rest as being inactive. And you can see that, especially when we make this strictness tighter, so yeah, so the activations become more sparse, that HypCBM is able to yeah, almost double or more than double the score of the Euclidean baseline. Then, as an ablation, we also measured hierarchical consistency for a hierarchically fine-tuned version of CLIP. with the note that this one is trained on 20 times more data, just like the OpenAI clip checkpoint. And I think this table shows two things. So the first is that if we compare these two, this is LFCBM with the 20 million clip model and the 400 million clip model. You can see that data scale really helps a lot in improving hierarchical consistency. From at this strictness, for example, it's from 0.28 to 0.41. And that also using this hierarchically fine-tuned version of clip really helps a lot with hierarchical consistency, as you might have expected. But interestingly, despite this 20 times data difference, we still managed to outperform this hierarchical baseline at some points, and yeah, score pretty similarly in other strictness. Okay, and then onto our intervention experiment. The idea here was to test intervention responsiveness. So to progressively suppress the activations of concepts for misclassified samples, and then to measure the confidence decay the models, both the Euclidean and hyperbolic models show. And we did this with three strategies. The first one being we deactivated the top contributing concept. Yes, I know.
Yeah.
Yeah, I see it on the top there when stop sharing.
There you go. Now it's back. Thanks.
Yes. And this one is the manual strategy where we manually look at the top activations and disable the highest contributing one that's not present in the image. And you can see that, and then as a third baseline, we also did to randomly deactivate a concept. And we observed here that deactivating this random concept doesn't provide negligible differences for both the Euclidean and hyperbolic models. So we plot here on the y-axis the original class probability of the misclassified class. And then on the x-axis, you see the intervention strength. And you see that because of HypCBM's intervention propagation mechanism, that a lot of wrongly or sort of misclassified concepts will be automatically suppressed, and therefore this results in a more efficient reduction in confidence. And this, I think, shows a nice example of this intervention propagation, where the ground truth is locker room and the model has predicted server room, which from this image I might have done the same. But if we here intervene on the words electrical equipment, if we only intervene on electrical equipment, our model still predicts server room, the wrong class, because circuit breaker and technical equipment are still highly active in this case. If we propagate this intervention to circuit breaker and technical equipment, which our hyperbolic VLM sees as children, then we see that the model does flip to the right prediction. And then we measure concept stability and robustness. And the idea here was to not only measure robustness at the prediction level, so is the class still correct, but also at the concept level. So in a corrupted image, do we still show the same, are still the same concepts activated as in the clean image? Robustness we define here on the y-axis, we define as accuracy under the corrupted inputs. And the corrupted inputs are any, here I show three examples. So Gaussian noise, motion blur, brightness. The types of corruptions are shown here. And concept stability we measure as the Jacquard similarity, so the intersection over union between the set of clean or of concepts present in the clean image and the set of concepts present in the corrupted image. And we can see from this plot on the right that HypCBM has a higher robustness in 13 out of 15 corruptions and an average stability improvement of 0.3. So for the Euclidean models, very often the amount or the concepts that are present in the corrupted image are very different from the concepts that are present in the clean image. Yes, and of course there are a few limitations of our work. The most important one, I think, is that our model struggles a bit with fine-grained classification. We did also try uh, using the CUP 200 bird classification data set, but we found that yeah, like multimodal models in general struggle with fine-grained classification. So if we show it an example of a very specific type of bird, and we want to distinguish it from other very specific types of birds, then like the top contributing concepts will often just be bird and forest and things like that. Then also there's the distinction between WordNet, which we use a lot in our evaluations, is a taxonomic hierarchy. And if we're gonna, yeah, if we want to classify concepts or classify images based on concepts, we're more interested in a visual hierarchy. So something that might be a parent-child pair in WordNet taxonomically might not be in, yeah, visually. And then finally, we also have the backbone dependence. So the performance of our models is limited by hyperbolic vision language models, which are still in their early stages. But yeah, we also see this as a nice outlook for future work, because as these models continue to improve, yeah, our method can naturally scale along with them. So yes, to summarize briefly, concepts are not independent, so we shouldn't treat them as such. Hyperbolic space is naturally suited to embed these hierarchies that concepts are structured in. And I think the main takeaway from this work would be that embedding concepts in a manifold that reflects their hierarchical relationships well leads to explanations that are more accurate, robust to corruptions, hierarchically consistent, and additionally allow us to intervene on misclassified concepts more efficiently. And another takeaway is that interpretability is truly shaped by the representational geometry and not just everything that happens afterwards. So yeah, I would encourage you to try out alternative geometries that suit your needs, because concepts are highly structured, and hyperbolic deep learning provides a very nice, efficient framework to work with this. So yes, that was it. Thank you all for listening, and I'd be happy to take any questions.
Fantastic. Thank you so much, Daniel. That was very fun. And cool, yeah, thanks. Do we have any questions from anyone?
I can ask a question. So, Daniel, so you were saying basically, my understanding, the two difference that you made here is you changed the encoder to a hyperbolic encoder for text, and you changed the VLM to a hyperbolic VLM.
Yeah, so basically our VLM is something like, you can see it as the hyperbolic version of CLIP, basically. So it's a text encoder and a vision encoder. And then on top of this, we modify, so instead of using cosine similarity as our activation, we use the entailment thing.
Yeah, and so basically, you were saying like if I'm not really aware, like I don't know this kind of literature a lot. So how the difference between like that regular hyperbolic VLM versus like a normal VLM and like on benchmarks, is it like a lot worse or is it better in general? Like
It is.
without.
So if we compare the accuracy for this 20 million, this model trained on 20 million pairs, we see it's often a bit better than CLIP, even.
Okay, so
And then on top of this, we get all these benefits of like hierarchical embeddings and yeah, and other things, basically for free.
okay, so basically you would expect that it would scale exponentially when these models become even more better in a sense.
Yes, maybe not exponentially, but I would expect the gains to, like, yeah, there's just not a lot of literature on hyperbolic vision language models, but I do expect them to improve.
Is there
And
like a problem why people don't train these models more often? Are they like less stable? Is it?
So one of the issues is that if we consider this Poincare disk, like if you're at the boundary, for example, on this Poincare disk, the distances, if you're exactly at the boundary, the distances are infinite. So this leads to usually also you need to train hyperbolic models in double precision, because these coordinates that range from 0 to 1 will get very close to each other. And also it requires more memory sometimes, because just addition in hyperbolic space needs, I think, about 4 different variables, whereas in Euclidean space you would only need 2. So there are a bit of computational constraints that are the main reason I think that these things have not scaled yet. But yeah, things are looking promising.
Thank you.
Yeah, I may have a bit of a following question or follow up on that. So, like, obviously, like, I guess if you're changing the backbone compared to say the level 3, which is the main baseline you compare against, you change the backbone. Like, I don't know, I don't have a clear answer for this, but what's the best way to disentangle between what comes because you use a different backbone and what comes from the actual geometry change?
Yeah, so this is a bit of a hard question that, like, to answer this, we would have to train, I think, a hyperbolic vision language model with cosine similarity, basically, because then we can truly compare the 2 models. But like as of now, there isn't a Euclidean model that's trained in this way. That would truly, like, that would be the best disentanglement, I think. But so this baseline, this clip RE one I showed, that one uses something that's similar to entailment cones, but then on the hypersphere. So there you would have that a general concept would be in the middle of a cluster of concepts, and then using these entailment relations, we so then they also enforce some sort of hierarchy there. And we see that we also did an ablation where we tested just the accuracy of this model. And although it did perform much better on the hierarchical benchmark, it scored much worse on the accuracy benchmark.
So do you know, like,
I see.
like, go ahead. Okay, I think it was cutting.
I think you froze.
Yes. Yeah, so I was like saying, so basically what you just said meant like, okay, if we don't know, if there's not a hierarchy, it doesn't perform well, right?
If there's not a hierarchy in concepts?
Yes, in this case, because the accuracy
Yes.
dropped when. Okay, so
Yeah. So one explanation I have for it is that if we have if we use the standard COP concept or attribute bank, things like spotted wing and white feathers they're not really hierarchical. So that makes it hard to specify this.
okay,
I
so
think.
we basically need to think more about the concepts we have when we're doing.
Yes. But like to add to that, like in general, multimodal approaches, like also the label-free CBM performs pretty poorly on CUP, for example.
Yeah, I've seen that as well from experience.
So I think yeah, sorry.
No, keep going.
So I think if these vision language models would be more accurate at representing these fine-grained attributes, then of course it will scale to these methods as well.
Sorry, and I actually have a maybe clarification question, because I think I might have missed the gist of it, like the more sort of technical sort of thing. How do you actually construct a hierarchy? Like, once you train this hyperbolic model, how do you actually construct the hierarchy? Is that something that you generate with BoardNet, or is that something that you evaluate with BoardNet, or both? I wasn't sure which one of those.
Okay, so we have image text pairs,
Yes.
and we're basically gonna do so. This mirror, I can show you on my screen. I have a diagram of. So yes, okay, this hierarchy is implicit. So we're not using any labels of this is a child or a parent concept. We're just doing, we're just making sure this image embedding falls within the entailment cone of a text embedding. And then on top of this, we also do contrastive learning. So there's two losses, this entailment loss and a contrastive learning loss. And this basically makes sure that, and especially in HypCLIP here, where we also have the fact that specific text instances, which here are defined as text boxes, are more general than the entire sentence. So the entire sentence could describe something very specific. For example, the glass is on the table, and then text box would be only the glass, which of course could appear in many different types of sentences.
Yes. But then from there, how do you actually reconstruct the hierarchy? So I understand how it can be captured implicitly in the geometry. But if you want to say, like, what is the geometry that your model is capturing, and what is the hierarchy that your model is capturing, how do you determine that?
Sort of how do you read it out, you mean?
Yeah, how do you read it out exactly?
Okay, so that there's not really, yeah, that's a difficult question. But you can't really read it out directly, but I mean, just like with vision language models in general, you can do latent space visualizations. But yeah, so like this norm at least encodes where, how deep in this hierarchy a concept will be. And then using these entailment relations, you can, or yeah, coordinates in general, you can see if they're, yeah, entailed by their parent concepts. But there's not really a way to like visualize the entire hierarchy this way.
Fair. And then so then when you propagate an intervention, how does that propagate? So how do you determine, I'm intervening in this concept, and this concept entails this other concept, therefore I should propagate it? Like, how is that process determined?
So we only look at whether a child concept is entailed within the entailment cone of a parent concept.
Okay.
And that we do by just measuring the exterior angle and the cone aperture.
And you do that sort of like just by looking at all concepts and seeing which ones are within, like,
yes,
the concept of, okay, I see.
Yeah, yeah.
Okay.
And it's very fast as well, because usually we're not using that large concept banks.
Nice. That's very cool. That's super interesting, actually.
Thank you.
Out of curiosity, the sort of, well, I forgot the name they used, the margin of inclusion, I think you called it.
Yeah.
Is that a standard activation? Is that something that you guys came up with?
No, that was something we came up with.
Okay.
It's sort of like the idea was to create sort of the cosine similarity activation, but then in hyperbolic space. And the thing I tried first was also to sort of draw a straight line from the origin to the text embedding, and then to see along this path, are there similar concepts along this this axis? But this turned out to work a bit better.
Nice. That's really cool. Do we have any other questions from anyone else? If not, I don't see anyone. Yeah, if not, well, thank you so much, Neil. It was super interesting. Also, particularly for me, I'm super. I think I've touched hyperbolic geometry once in my life, so this is always good to have a bit of a
you should
an actual application of it. It's very nice. So yeah, really appreciate it. And yeah, thank you so much, everyone, for joining. I think we're gonna have we have one next week. It's gonna be Naveen. So Naveen is gonna be talking next week sometime. So please join if you can. Otherwise, we'll hopefully see you very soon. Right.
Thanks for inviting me.
No, thank you, Daniel.
Thank you.
Bye.